Alright, so last day, and after pre-stuff, I think we're kind of like about 10-15 minutes, so this will be short for me too. Last time I kind of pre-gamed a little bit of the stuff. We wanted to talk about how you can assess performance on things, and so I talked a little bit about those. There's a few basic ways you can do them. Like anything else, there's synthetic benchmarks that you can do. A synthetic benchmark is going to be, you take a variety of different kind of preset, run this application, that application as it goes on. These are not as prolific on multiprocessors as it goes, particularly if you're dealing with a larger system that's out there. And part of that reason is most of the synthetic benchmarks are kind of aimed at a broad range of user interactive type programs. And so they kind of select portions of ones that might be used, even, I mean, like Pro Engineer or stuff like that will be in there, just some of their CAD operations or some other stuff. But those are not the things you do on a cluster when you're going to larger performance things. So it's theoretically possible to have these. There are some matrix multiply ones you could do and things of that sort. But that's one possibility. People will use, you know, kind of Amdahl's law type of stuff that goes on. And it's usually done in a highly simplified ways, and there's a lot of complaints that go on. So let me just kind of briefly cover those areas that go in. If you remember that you have the basic thing of Amdahl's law says, you know, 1 is the original timing that you had, and then you have, you know, a fraction of your code that can be sped up, and a fraction of your code that can't be sped up. And then on the bottom, you have what was the speed up of that area. But we can use this for parallel processors, and what we do is we assume that your code that you have has kind of two basic sections in it. So if I've got, imagine this is my block of code, you know, I have a sequential, and then I've got a section of code that's parallelizable. And then I've got a little sequential section and a section that's parallelizable. And I just assume that it kind of goes down in that type of a pattern that's on. Now, under that assumptions, with multiple machines, I can take the parallelizable section, I can break it up into an appropriate number of sections as much as I need to, but I can't break up the sequential. Now this is often done with like barriers. So this is mentioned, some of the ones, there's, you know, some of the memory areas that would use this. The compiler, you know, talked about the fact that you had some of these areas and you put barriers in, and there was atomic operations and non-atomic operations. Those atomic ones are usually used to create these barriers to stop everybody at a point, synchronize and move on. And that's actually slow and sometimes dangerous depending on how you do it. That's going on. Sometimes you have no choice because you're trying to synchronize your memory or the algorithm forces it. So assuming under this area, if I were to split this into 3 pieces, I could take this and get a speed up of 3, but only in the sections that are parallelizable. Now, that means that this is the number of processors that's available to you. So maybe I should put P down here, you know, for the processor count that's going on. So you have the ones that are sequential, and I've got the ones that are basically parallel operation. Now, you know, this actually gives you an overall fairly, you know, almost you know, it's a fair assessment in that it usually ends up being an underestimate if you do a good job. Okay? So it gives you a good limit to say, are you decent? Now, could you do worse than this? Absolutely. I mean, it's you know, very easy to go down with these. Where the challenge comes in and why this one doesn't always give a great job is, notice I split this up and I've got some transmissions and things that have to go on, but I didn't give you anything for the communication delays. Once I go to multiple machines, I have to distribute data, I have to go back and forth. That's going to create time penalties that go on to them. So in some sense, this gives you, you know, some idea of a limiting function of what goes into it. Now, there are some other things that can happen on here. This assumes that I can only do one or the other also. There are times when I can, you know, parallelize something up to a very high degree in certain areas and a lesser in others. So what do you do if I've got like a tree? Right? On the first step, I can do n, and then, you know, each time I have it, n over 2 as it goes down. It's not easy into this. Now, you know, that ends up giving that this fraction, I can approximate that by saying that it happens log n of the time. So I take the tree and I kind of flatten it, but that's not always a fair assumption either. So that's why I say there's some cases where you can do better than this, there's some cases you can do worse, because it doesn't account for all those areas. But what it will do is it'll give you a ballpark. And in that sense, it's actually useful. A lot of people are very negative on the use of Amdahl's law on this. But I'll tell you this, you should never count on that as a useful number. Other than this, it'll get you somewhere in the zone that you can do something more intelligent from. All right, so if I'm doing a quick back of the envelope thing, it's not a bad one to go towards. So, you know, I've got synthetic, I've got the Amdahl's law, and then the other one, and I think this is actually, in some sense, the most useful one, which is I benchmark it based off of the actual application you're going to use. Now, this is a completely crazy statement if you're talking about a laptop or a desktop machine, because you're not going to use one application. You're going to use a whole ton of applications that go on. But on your cluster, you're probably only going to have a few applications that go on. Right? There may be some other side ones that happen as well, but those side ones are not the bread and butter of that cluster that goes in. Right? You know, NASA's stuff that goes on, you know, they will buy one and it will be set for, you know, say for instance, aerodynamic equations, hypersonic fluid flows. So I've done some of that stuff with NASA Dryden and helping one of the professors here, Dr. Cool, with his stuff that's going on. And it's aimed at that. And everything that cluster is used for is for that purpose. And some people might say, hey, can I run my code on your cluster, you know, during downtimes? But honestly, this sounds horrible. You don't care what their performance is. You bought the cluster for this other thing, and then there's some spare cycles, and so you let people use it. If you were doing it for galactic formation problems, you'd be doing something like Barnes-Hut or something else. You would do it for Barnes-Hut. If you bought this to do environmental simulations, to take a look at, you know, atmospheric conditions and weather prediction, or, you know, tidal wave prediction or whatever, that's your main application. So there's, you know, 1, 2, maybe even 3 applications you're going to really run on your system. And so it's practical at that point to actually look and say, how would my system function on those, and scaling wise what's going to happen. That's really what we're trying to do with these. Now amongst these, there's kind of 4 archetypal problems that are out there. I believe the book does mention all these. They're all also in my online notes, what the scaling factor is. So I'm going to give you a brief overview of them, why you care, where they go, performance, and then with time constraints, I'm just going to sketch what it is. There are some work problems on there. So I'll sketch what you have to do in the work problems, but I'm not going to walk through the numerics because it's really just a matrix solution. It'll be fairly straightforward. So the trick on this is this. We've got different problems. I've mentioned one, which is ocean, that's going on. Ocean, this also works for atmosphere and things like that. Basic idea is as follows. Get a pen that writes. So I take a grid that's out there, you know, there's some pattern, you know, of land around it, I've got ocean in between. I'm going to take a portion of this, assign it to a particular machine that could have a whole bunch of data points in it, where you're going to exactly solve for the ocean height that's going in. And, you know, each machine is going to take its portion of what's going on. So if I want to track a tsunami or model a tsunami propagating across the ocean, boom, I've got a great way of doing it. I assign a portion to them. Since the ocean just has to match at the boundary, I only have to have, if I was dealing this machine, it only has to send this information to this machine. So it's only a fraction of its data, easily discernible, and it knows exactly who it's going to send to, and it doesn't have to send very far, because you only have to match at those portions. So it's a very simple send to a very limited group of machines that can go on. Well, if you consider that, let's say I was doing a square array that's going on, right? So I could have n different node points on the side. I've got n squared of these that's going on. So I'd be looking at n squared things, p processors, that's how many of the nodes that you have going in. Right? If you were doing it, if you said, hey, look, there's a total of n nodes, counting every single data point, because sometimes you count them by those, then you would just say there's n total points you're evaluating at. Instead of counting on a side, you count the total number, it'd be n over p. Right? My point to you is that it's fairly straightforward to figure out what is the computational requirements that go on to them. The data transmission ones, since it's the exterior side, complexity, we don't care about a scale factor. Since these are going to be fairly square, it's reasonable to actually approximate it by the diagonal that's going on, which would just be the square root of the total number of nodes that's going in. So your data is on there. And the reason why we often do it square is that if you have a long, thin one, then your total transfer that you have to do is based on the area, or on this well, it technically is a surface area because this would be a volume coming up. But you can consider it the outside edge, and the interior is where your computation is. Well, this is going to make your data transfers fairly proportional to your amount of computations you have to do. Your best efficiency is when it's square, right? Because you have a lot of interior stuff that doesn't have to do transmissions. So you get a high amount of computation per transfer data on this setup rather than this. So we're always trying to make them square, which is why the diagonal is a very good approximation. Make sense? And then, of course, you split that across the processors. Go ahead. So that's what Ocean is, how it scales, and we're going to break it into two numbers. You worry about how does computation scale and how does its communication scale. The second one, when we're talking about what data you have to transfer, addresses that second weakness, that you don't include any information about how the communication goes. So other ones that we've got. So we've also got, for instance, LU factorization that goes on. LU factorization is a nice stand-in for a wide variety of different other factorization methods that are out there that's going on, and LU is fairly common. LU just takes a matrix and breaks it into a lower matrix component and an upper matrix component that if you multiplied them would equal the original. So if I take an A, I say it's equal to a lower matrix times an upper matrix. This is just lower triangular, and this is upper triangular. This is the first step that goes into Gaussian elimination. So if you're trying to solve, AX equals B, which is like a gigantic portion of the computations that are actually done out there in the world, this is almost in every matrix calculation you do, this step occurs. And so this is a way of breaking it. This is Gauss's method for doing it that breaks it into two lower things. It's extremely fast. It's numerically sensitive. So it's a time accuracy trade-off that goes into it. Usually if you consider the size of the matrix, the calculations are proportional. So generally matrix operations are n cubed that goes into them. And the communication requirements is going to be proportional to the number of elements, which in this case would be proportional to kind of n squared that goes on. And then again, split across all the different ones. We often do FFT also that goes in. So FFT that happens, this is kind of one of the famous ones. If you do just convolution, right, that's going on, that's proportional to what a basic Fourier transform is, and that's n squared. So if you have n data points and you need to convolve them, all possible things, you get all combinations between them. So you get n squared. So a regular Fourier transform would be n squared. And then what happens cleverly in here is how do you get them all to combine together with the weights? And what they did is they did what's called a divide and conquer algorithm. Divide and conquer, if you ever see anything that looks like n squared, immediately think divide and conquer algorithms. Because if you have something that's n squared complexity, there is almost always a divide and conquer algorithm that will reduce this to n log n. Right? This is one of those, there's 4 basic types of algorithms in computer science, that's it. Right? And this is one of those big ones, and it's a really nice advantage that goes on to them. So, you know, FFT, just considering the basic linear one, we've got n log n as its complexity of growth with problem size over the number of problems p. Now, if you consider what's going on with these, you've probably seen has everybody seen FFT, how it goes? And you have these basic, if you take a simple FFT, each one of these is going to have to the next level inside the tree, right? They have to do their communication. You get these little butterflies, we sometimes call them. That goes on, and then the next level it's going to switch between these ones. And you'll again get a butterfly, right? And same for the next group in. And by doing this, you will very rapidly, since this one's effect came into here, it gets all the way down. So what you end up, if you just consider one of them, you get a tree. And then you just have a bunch of trees in parallel. But the in parallel doesn't cost me anything. So really it's just a tree, which is where the log n part comes in. But that means at any given time period, half of my data is being switched. So that means communicationally, it's n over 2, which is just n over the number of processors. So it's very easy to grab that one as well when you're walking through. So if you're familiar with FFT, it's easy to grab it. And again, this is very common in transform techniques and an awful lot of linear systems work and things of that. So if you're doing a lot of that, this is a good benchmark to calculate where your cluster do well. Last one that's out there is Barnes Hut. That's a kind of a good benchmarking one. This one's galactic formation, so a basic fundamental physics problem that goes on. It shares a lot in common with FFT in that it will do a type of divide and conquer that goes on. It shares some things in common with ocean because it's breaking up space into regions that goes. So you'll see a little bit of factors of each. And what they consider in that area is, imagine now this was space that's out there. And I'm considering for galactic formation how any of these particles is going to be attracted or pulled together by gravitational effects. Well, there is gravitational effects from here affecting a particle way over there. But if you consider the effect of all these ones here, I can actually sum them together as a net mass from this processor. So I can reduce the amount of communication across the processors because at a distance they're not going to affect. But there is some complexity that goes in because if I have them really close, I can't do that. The unique effects of these that go on, because what they're actually considering is microscopic effects that go in. So if you're right at that boundary zone, there is some area that we care about for how they're going to combine together. Right? So if you're right next to a particle and we're trying to see if things are clumping, you don't just want to consider it as part of a remote source, even though under a Newtonian assumption that would be true, but the universe isn't Newtonian. It does actually take time for gravitational effects to propagate, gravitational waves, because of relativity. So therefore you can't do the lumping effect everywhere. Relativity prevents that. So Barnes Hut will cover those type of areas. And it also, so it'll have, it's n squared log n, if I remember the effect that goes in, because it gets a little bit of areas off them. Computationally or communication, they have some. But what you do is I have 2 of these different ones. I know how they scale. Each one of these, like for instance, if I was doing FFT, you know, let's say the coefficient for this was alpha and the coefficient for this was beta. The time that it takes is going to just be that. For n being your problem size and p being your number of items in the cluster. So this is the equation, but you don't know alpha, you don't know n, p, you don't know b. So how do I get them? Well, I can pick a particular problem size, some test sizes that are reasonable, and I can make a smaller cluster, but that's still reasonable size as a cluster. And I can try a couple points here and a couple points here, and I'll get some time estimates. And then the only thing I don't have is alpha and beta. And each one of these time estimates gives me a row inside my matrix. So what you end up with is, you know, you'll get this, you knew it, so you can calculate a number, and so that'll, you know, become whatever, some x, right? x0 for the first one, and y0 for the first one of this, for some particular problem setup, and there'll be a t0. And this matrix times alpha beta is going to be equal to this T matrix. And you just do that for each one. You set up the next problem, x, y, y, in a T1. You can do a bunch of these. This now just becomes A unknown x equals B. Same exact problem again. You can actually do this inside MATLAB very easily. Call this A, call this x, call this B. It's small as it goes. So just go x equals A slash B. And it will give you what your coefficients alpha and beta are. Now you know alpha and beta for your problem, for your type of hardware. Now you can say, hey, look, I want to find, for instance, a common one is, I want to be able to finish something in a certain amount of time. I know how big the problem's going to be. I want to figure out how many P's that is. All right? So now at that point, you know this one, you know this one, and you need to know these, but you only need it for one row that's going in. And the coefficients are connected that's going in. So you can take this same thing, the known T's, and you can find out what these have to be, but you then just group them together. All right? And you know what n is, so then the only thing you're solving for is P. You got one equation, one unknown. So it's fairly straightforward to do it. Now, these coefficients will be different based on what your network topology is, what your particular computational setup, if you do a particular, you know, if you're doing Xeons and, you know, versus, you know, taking some other, you know, type of processor, it'll be different. Different motherboards, it'll be different. Different NICs, it'll be different. You have to find for your setup the alpha and beta that's going on to do this accurately. But if you do, you should get a pretty good idea of how it's scaling, so you can approximate for your problem and say this is the right number. And that way you can pretty much guarantee your problem should fit in the time frame you did. So it's a good way to size a cluster. And computationally, it's a pretty simple problem. Right? This will take a tiny, tiny fraction of a second to calculate inside MATLAB. So it just takes a little bit of groundwork at the bottom. And you can get these timings by just pointing it on and doing a time measurement on your cluster. I would recommend, if you're going to run it, if it's a smaller size n, make it big enough n that it's reasonable. Because if the n makes your time too small, the time measurements are going to be no good. Right? It'll be too imprecise on where it's going off of. They're only accurate to milliseconds. So try to make your times run in the order of seconds to minutes. You know, and then do a few ones that'll scale across time so you can get good measurement of the effect of these to fit it or remove any noise areas. If you do it, you get a pretty good ballpark. I've had a bunch of people do this, and it's worked fairly well for them. All right, any questions on this stuff? Oh, awesome. So we're done then?